Mathematics forms the core of data science and machine learning. Thus, to be the best data scientist you can be, you must have a working understanding of the most relevant math. Getting started in data science is easy thanks to high-level libraries like scikit-learn and Keras, but understanding the math behind the algorithms in these libraries opens an infinite number of possibilities up to you. From identifying modeling issues to inventing new and more powerful solutions, understanding the math behind it all can dramatically increase the impact you can make over the course of your career. Hi, I'm Dr. John Krohn, a best-selling author on deep learning and host of the Super Data Science podcast. Today, I'm here to help you do more than ever before with my Mathematical Foundations of Machine Learning course. Over the years, I've identified a body of underlying mathematical knowledge that is critical to being an outstanding ML practitioner. Until now, there has never been a hands-on, application-focused course that concentrates all of this essential math into one place. Together, the specific subject areas we'll study are linear algebra and calculus. Each topic in these subject areas is brought to life via meticulous illustrations, easy to follow full-color equations, comprehension exercises with fully worked solutions, and hundreds of code demos in all of the most important Python libraries for machine learning math, specifically NumPy, TensorFlow, and PyTorch. All of these code demos will be extremely easy to run from any web browser with absolutely no installation required. Access more than 15 hours of math content, including exclusive fully worked solutions to exercises that can't be found anywhere else. Ready to enrich your appreciation of ML and develop limitless possibilities for modeling data? Sign up and you can get started with me right now. Hi there, this is John Krohn. Welcome to my Machine Learning Foundation series. This is the first subject in the series. It is Intro to Linear Algebra. This is an interactive primer on the theory and practice of tensor manipulation in Python. And here is a wonderful illustration of my puppy Obo by the illustrator Hagley Bassens. So in this Intro to Linear Algebra, we are going to have three segments. We're going to talk about data structures for algebra. Then we're going to cover common tensor operations with tons of hands-on examples. And finally, the final subject in this subject is matrix properties. We're going to kick off segment 1 in this video, data structures for algebra. All of the topics in here are what linear algebra is, a brief history of algebra, tensors, particular types of tensors, including scalars, vectors, simple manipulation of vectors such as transposition, ways of characterizing vectors like norms, and special types of vectors like unit vectors, more special vectors, basic, orthogonal, and orthonormal. We're going to tackle building vectors in NumPy and other types of tensors, as well as matrices, tensors more generally in TensorFlow and PyTorch, the two most popular automatic differentiation libraries. In this first video, we're going to talk about what linear algebra is and just do a single slide on a brief history of algebra. You'll have to wait for future videos for the rest of the content. So what is linear algebra? Well, first let's talk about what algebra more generally is. So algebra is arithmetic that includes any non-numerical entities like x. So here's a simple example. If we have this equation, 2x plus 5 equals 25, well, we can subtract 5 from both sides of the equation, and then that will leave us with 2x is equal to 20. We can then divide by 2 on both sides, leaving us with 10 is our answer. And you can confirm for yourself that x must be equal to 10 because you can plug it into the original equation, and when x is equal to 10, 2x plus 5 comes out to 25. It's the only solution to this equation. So that's what algebra is. Now, to dig into what linear algebra is a bit more, it isn't linear algebra if it has an exponential term. So for example, an equation that has 2x squared plus 5, well, that isn't linear. It's a nonlinear transformation. And then a square root, that's also a nonlinear transformation. So this equation is also not linear algebra. To give you a really nice and tidy definition of what linear algebra is, we could say that it's solving for unknowns within a system of linear equations. So let's talk about that idea of a system of linear equations, multiple linear equations, where we're solving for unknowns like x across several equations simultaneously. So here's an example. Let's say a sheriff has a car that travels at 180 kilometers an hour. A bank robber has a slightly slower car, it goes 150 kilometers an hour, but that bank robber gets a 5-minute head start on the sheriff. So how long does it take the sheriff to catch the robber? And what distance will they have traveled at that point? For simplicity, let's ignore acceleration, traffic, etc., and we'll just assume that they're traveling in a straight line in one direction. So we can solve this problem graphically with a plot. We can note here that 150 kilometers per hour corresponds to 2.5 kilometers per minute, and 180 kilometers per hour corresponds to 3 kilometers per minute. We can plot things out here, and so we have a plot of time along the x-axis, the horizontal axis, in minutes, and then we have a plot of distance in kilometers along the vertical axis. You can see here there's a green line corresponding to our bank robber going 2 kilometers per minute. So that's a particular slope. And our sheriff is traveling at a faster speed, so has more slope, a slope of 3 instead of 2.5, corresponding to 3 kilometers per minute instead of 2.5 kilometers per minute. And then we have our 5-minute head start to the bank robber accounted for by the gap here along the x-axis. So what we're trying to solve for is this crossover point, where the sheriff catches the bank robber. So what time is it? How many minutes have elapsed at that point? And what distance have they both traveled at that point? So you can see that graphically you could come up with a solution here. Alternatively, we can solve the problem algebraically. To represent the bank robber, we can have this first equation, which is distance d is equal to 2.5 times time. And then a second equation representing the speed of the sheriff. However, we also take into account that 5-minute head start. So we have a penalty of 5 for the sheriff. Now, both of these equations are equal to d. So we can actually set this term here equal to this expression here. So 2.5t is equal to 3t minus 5. You can then multiply the 3 into the brackets to expand out this side of the equation. And then we start trying to isolate t by moving 3t over to the other side of the equation here. So we subtract 3t from both sides of the equation. When we do that now, 2.5t minus 3t gives us a negative 0.5t is equal to negative 15. And so now we can divide both sides of the equation by negative 0.5, and that isolates t completely, giving us a time of 30 minutes. So now we know how long it takes for the sheriff to catch the bank robber. To figure out distance, this is really easy now that we've solved for t. We can simply plug that 30 into the t in either equation. So for the first equation, 2.5 times t, 2.5 times 30 is equal to 75 kilometers. And then we can plug it into the second equation too. So 30 minus 5 is 25, and 3 times 25 is 75 kilometers. Of course, we get the same answer because it is a system of linear equations. Now, that was a nice, neat, and tidy situation where we had one solution. However, there would have been no solution if the sheriff's car were the same speed as the bank robbers. So if they both were traveling at exactly the same speed forever, then there would be no solution to this problem. On the other hand, we could also have an infinite number of solutions if both the bank robber and the sheriff were traveling at the same speed and had the exact same starting time. So their slope is the same, Their start time is the same now. They overlap at every time point. These are the only three options in linear algebra. So you either have one solution, no solutions, or infinite solutions. It is impossible for the lines to cross multiple times. So this is a key part of this being linear algebra in these systems of equations. In a given system of equations, there could be many equations. There could be many unknowns in each equation. In the example that I just showed you, there were two equations and there were two unknowns. However, let's consider another example here where we are building a model. Specifically, this is something called a regression model, which I'll get into a little bit of the detail here in case you're not already aware of it. In this model here, we are trying to predict house price. So we have, for a given house, we have its price that we're predicting, y. And then we also have a number of features or variables that we are collecting to try to predict that house price. And in a lot of cases, the more features that you have, the more accurately you're going to be able to predict what you're trying to predict, the more relevant features. So some of the relevant features here might be distance to school or number of bedrooms and so on. I have M features here. And so B, C, and M, these are examples of features. This could be an integer, the number 3, distance to school could be a value like 2.5, representing 2.5 kilometers. And so on for however many features we have, in this case, M features. We also have to have a y-intercept here. So this is one last variable. It allows us to, across all of the house prices that we have an average house price. And without this y-intercept, without that kind of average baseline, before we start factoring in the other features, it becomes much more difficult to fit a good model. So here we have many unknowns, and we could have effectively unlimited rows where every time we get a house price and collect the pertinent information associated with that house price, like distance to school, number of bedrooms, and so on, that's another row for our system of equations. It's typical in machine learning problems, even a regression model like we're looking at here, to have thousands of rows representing different houses. So n rows, we could have thousands of rows here. And maybe a dozen features. So M could go up to 12 columns. In a typical deep learning model, in contrast, it would not be uncommon to have millions of images, say, for a machine vision model. So we'd have millions of rows in our set of equations, and millions of columns representing millions of parameters. Potentially high-resolution images would have a lot of pixels. So here's that equation from the preceding slide. I've now generalized it to a lot of different houses, n houses. And I've made it into a set here using set notation from linear algebra, these square brackets. And so for any house I in the data set, so we can call that particular price yi, which could be, say, $300,000 or what have you, then xi1 to xim are all of the features for that particular house I. Now, across this whole system of equations, we were trying to solve for the parameters A, B, C, and M. Y is our outcome that we're predicting, say a house price. X is the variables, the actual values that we have associated with that house price. So x11, x12, x1m, and so on throughout this set of equations. And these parameters, A, B, C, and M, these are the unknowns that we're trying to solve for. And you'll notice these unknowns are consistent across all of the equations. So whether we're talking about the first row, the second row, the nth row, A, B, C, and M are going to be the same value. So we're trying to find an ideal value to represent all of the rows in the data set for each of the features, each of the columns. I have some quick examples to show you here of how this looks in practice. So if you go to johncrone.com/deeptf1, this brings you to a deep neural network in TensorFlow. And by the end of this whole machine learning foundations journey, a lot of what's happening in this notebook will start to make sense. Early on in this journey, I'm not expecting this stuff to make sense. The reason why I'm in here, though, is just to show you that this same kind of thinking that we had on the slides from linear algebra applies as well to various algebraic objects. What I'm going to introduce momentarily is tensors. So we have vector tensors here, one-dimensional tensors, and matrix tensors, two-dimensional tensors here. And so we have inputs. These x's are our inputs, just as they were in the preceding example. So these x's are inputs into the model that we're using to predict the outcome y. In our deep learning model, in this particular model, it's a machine vision model that's being passed in 784 pixels per image. So we have this vector of 784 pixels being input, and we're using that to predict outcomes. This y variable here, this vector of length 10. And in the middle, we have these things called weights and biases, weights matrices and bias vectors. The specifics of that don't really matter, except that these are, I'm just trying to show you some linear algebra data structures. And these are encoded in whatever software language that we're using. In this case, this is TensorFlow here. And so we create bias vectors, B1, 2, 3, and B out, corresponding to B1, 2, 3, and B out, these vectors here. And then we also have weights, so of a particular shape, W1, W2, W3, and W out. So these are these matrices with these particular dimensions. So this is just an example of how we're going to have various parameters, in this case weights and biases, that are going to be tuned by our machine learning algorithms in order to be able to map some particular pixel inputs into a prediction of what those pixels being input represents, some particular outcome. So this is just a slightly more complicated situation than we had with the linear regression example. And we can take it just one step further by showing that these linear algebra objects don't have to be two-dimensional. We can have higher dimensional linear algebra objects, higher dimensional tensors. I'll explain all of this terminology in more detail in the next video. But for now, it suffices to say that we have these many-dimensional convolutional objects that are specified by many dimensions. And these allow for some especially powerful machine vision models called convolutional neural networks. Anyway, just want to get you excited about what we can do with linear algebra. These notebooks, these TensorFlow notebooks, show you an endpoint that we're working towards in the series. For now, we'll focus on the fundamentals. Speaking of fundamentals, I find it absolutely fascinating to consider the origins of algebra. So let's take a quick moment here to do that. This guy here is Abu Jafar Muhammad ibn Musa, more commonly known as Al-Khwarizmi, because he came from a place called, so Al-Khwarizmi means the man from Khwarizm. And so this is a former center of Persian culture in modern Uzbekistan, today called Hiva. So in English, we pronounce this algorithmi. So this medieval Persian mathematician, who was around from 780 to 850 in the Common Era, was not only critical to the history of algebra, as I'll get to in a second, but is also the namesake of the word algorithm. So very prominent old mathematician. So algorithmi wrote the compendious book on calculation by completion and balancing. And in Arabic, this word completion is algebra. So algebra is actually right here in the name of the book. And completion and balancing refers to various ways that we can rearrange algebraic equations, some of which we've already looked at the beginning of this video. The medieval Islamic Arab Empire made most significant early contributions to modern symbolic algebra, so the kind of algebra that we work with today, although it was refined significantly by the French, such as René Descartes in the 17th century. Though that said, many other cultures developed their own approaches to algebra. So rhetorical algebra, the spoken algebra, was developed as early as 1900 BC by the Babylonians. There's an Egyptian papyrus dated to 1650 BC with linear algebra on it, so we know they were up to some algebra. Indian mathematicians were doing linear equations around the 6th century BC, as we know from some mathematical documents from then. And the Greeks, as long ago as 400 BC, were themselves doing geometric algebra, an example that we have here. So this was in the time of the philosopher Plato, and is a particular example of this geometric algebra here by Euclid in his book Elements. The Chinese had linear equations solved in a book from 250 BC. This book was called 9 Chapters on the Mathematical Art. And although the Europeans started much later in the late Middle Ages, initially by translating Arabic texts to Latin in the 12th century, by the 13th century, European mathematics rivaled other cultures. And when the Islamic Empire declined after the 15th century, European culture was left carrying the baton of algebra to today. This technique, devised initially thousands of years ago in some respects, and in its symbolic form many centuries ago by Persian mathematicians, we today have tons of contemporary applications that take advantage of lots of compute power and perform these algebraic applications in tons and tons of devices all across the world, billions of them, I'm sure. So one kind of straightforward application is solving for unknowns in machine learning algorithms, including deep learning algorithms. So this is our primary focus across this Machine Learning Foundations program. It's also used for reducing dimensionality. So if we have some high dimensional data, we can reduce it down using techniques like principal components analysis. We can rank web pages in order of importance. For example, with eigenvectors, we're going to talk about both eigenvectors and principal component analysis in subject 2 of the Machine Learning Foundation series called Linear Algebra 2. And same thing with recommender systems. So if you want to build a recommender for movies, for example, based on other movies that somebody has watched, you can use singular value decomposition to do that. And again, that is something we'll be covering in Linear Algebra 2 once we get past the foundational content in this Linear Algebra 1 course. It's also used to process natural language, with single value decomposition, or another technique called matrix factorization. And so whether we're talking about processing language coming out of somebody's mouth, the language sounds, or written language, we can be using linear algebra to be modeling topics, identifying what topics are being discussed in that natural language, as well as for semantic analysis. So in this Machine Learning Foundation series, this Intro to Linear Algebra subject that we're covering right now is foundational for, of course, the Linear Algebra 2 matrix operations subject that is coming up that will cover eigenvectors in SVD and PCA in. It also, I'm putting it in non-bold here because it also is foundational for, though not as directly as it is for Linear Algebra 2, for our Calculus 1 limits and derivatives subject, as well as for Calculus 2 on partial derivatives and integrals. It's also foundational for probability and information theory and Intro to Statistics. The only one that it isn't really providing much for is the Algorithms and Data Structures class, subject, which is subject 7. And it is very important, as basically all of these prior 7 are, for the final optimization class that will tie everything together and show us in incredible detail exactly how modern machine learning algorithms optimize. All right, up next, we are going to be introducing what tensors are. I've mentioned them a few times. We're going to dig into exactly what they are in the next video. See you there.